I'm so excited. I'm back in my classroom. Woo! Oh man, pumped. Place that makes me whole. Okay, kids, today we're going to go through some things on waves. I wanted to grab a slinky, which I did. You know, slinky, so much fun for like 2 minutes. You know, I mean, okay, fun's over. Well, maybe you try to make it go down the steps, and then it kind of falls and gets all tangled. Fun's really over now. Okay, but you know, for 2 minutes, slinkies are fun. But what you can also do with a slinky is we can show some of the, different wave properties. We had gone over a longitudinal wave and a transverse wave. And some of you are making drawings on those, on the wave notes. And they're not bad. But here, let me just quickly demonstrate for you what a longitudinal and a transverse wave would be. So if I take the slinky here, and I were to, if you were over there and I'm over here and I'm holding this and I send a pulse, one little energy burst, you can see boom, 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 boom. It goes back and forth. Transverse wave. Why is it transverse? Because if you watch one part, focus, you pick a slinky coil. Pick one, which one's yours? That one? Okay. Watch what happens to it when I send an energy pulse down. What happens to your slinky? The coil is going while the energy is going back and forth. So back and forth is perpendicular to up and down. So watch your slinky coil one more time, send one pulse, and we get a reflection. It's going back and forth quickly, but your slinky coil that you're focusing on is moving up and down. So that's perpendicular. So transverse, your particle motion, and that being the slinky coil, is perpendicular to the direction of the wave pulse. Longitudinal wave is just like this. So I take the slinky. This time I'm not going to send an energy pulse transversely. I'm going to send one longitudinally. That means in the same direction. So if I take a pulse and I throw it at this one, it kind of dies quickly when it hits my hand. But the energy, so you can see what happens. There is some compression going on. Watch, see if you can catch that with some of the coils compressing. See, you can see it. You can. Yes, you can. You're pretty smart kids. Yeah. Compression, bounce. Compression. You see that air compression. You get a compression coil. Coils compression. You get compression coils, and then you get stretching, and that's called rarefaction. There's a fancy word for stretching. That's what rarefaction means. So when I do a longitudinal, you get compression and then stretch. All right, so that would be a longitudinal. Well, what's happening there? Well, in a longitudinal wave, the coils are moving in the same direction as the energy pulse was moving. So I send a pulse to my left, your right, my left, your right, and then boom, you'll see the coils compress and stretch in that same direction. That's longitudinal, where the particle motion is parallel in the same direction as the energy burst. Okay, those are two different kinds of waves, and we should know that light, we have basically two different kinds of waves that we're going to be discussing here. Your light waves, as opposed to your heavy waves. Light waves, love it. Your light waves are electromagnetic. Okay, these are EM, electromagnetic, and this is transverse stuff. This is the stuff that goes through space where no one can hear you scream. And in space, okay, there's nothing there, right? That's what's called space. It's a vacuum. But yet the light can travel through it. It doesn't need stuff to travel through. Now, light can travel through stuff. Again, it goes through windows, right? You know that. Of course, come on. It goes through water. You know that. So that's stuff. So light can go through stuff, but it doesn't have to have stuff. Okay? Now, a longitudinal wave would be something like sound. Sound is a compression wave. And so instead of particle motion up and down, perpendicular to the direction of motion, in that case, you get your slinky coils, stretch them out, compression, stretch them out. Your slinky coils, I was using the slinky, but sound does the same thing. You get these areas of compression and stretch, compression and stretch. And this area here, the stretch part, called the rarefaction. I'll spell that for you. It's rare and faction. Hence, rarefaction. Okay, and so the direction of motion is in the same direction as the energy burst. Now with a longitudinal wave, you need stuff. You do need stuff. Again, space, nobody can hear scream because there's nothing there, and so sound doesn't travel. Oh, I've heard them talk in space movies. Yes, I have. Space movies are talking all the time. It's like, hello, Star Trek Enterprise to surface. Come in, Captain Spock. Hey, Spock, yeah. No, Spock didn't have a British accent, did he? Well, maybe if he did. If he did, he sounded like that. Okay, yeah, Spock, yeah, what's going on? And so they're communicating, right, through space. See? Lies. Somebody's not telling the truth. Probably you, because you are a nub. No. Hey, let's not get personal now. Come on. No, actually, they're using radio communication. That is, radio communication is a form of electromagnetic communication, radiation. And so that is using light technology. You don't need anything. Sound technology, you do. You ever watch Star Wars and things blow up, out in space and it makes a lot of noise? No, that wouldn't happen. You're not going to get sound traveling through space. So you need to have stuff for a longitudinal wave. Sometimes these are called mechanical waves. And a mechanical wave, well, that indicates that, mechanical indicates you need stuff for it to travel through. There's a compression that goes on. You have to compress material in order for the sound to propagate. Propagate means to keep traveling. So there you go. So you got your two different kinds of waves, your longitudinal or mechanical or compression wave. They all mean the same thing. And you have your transverse wave, which the best example of that is a light wave. Water waves are transverse for the most part. I mean, if you were sitting on the dock of the bay watching the tide roll away and you watch a duck sitting there and a boat goes flying by and it makes waves, the duck goes quack, 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 quack. As the wave goes by, the duck goes quack, quack. There is a little bit of a forward motion because there's some drag due to friction. But the vast majority of the energy is going to be transverse, quack, quack. Duck does this as the wave goes by. So water waves, another example of our transverse waves. Okay, let's move. So there are different kinds of waves and some examples of which ones they are. Oh, I cleaned these things out and they're not working as well. They actually worked better cleaning my board when they were dirty. And I get them all nice and washed here. Well, yeah, what are you going to do? You know what that teaches you? Never take a shower. You'll be better off. Clean things don't work as well. Yeah. All right, let's see what we got going on. Okay, so we got the slinky thing. And let's see. The next thing I want to talk about is resonance. Well, you know what? Let's see. I'm going to make this video longer. You know what we're going to do? We're going to cut this video short here, make a couple short videos this time. And so we'll end up this video on different kinds of waves, and we'll go to the next video on resonance. We'll do that next. Okay, kids, get yourself a drink of water. I need